Welcome back to another section of my YouTube channel tutorial. In this tutorial, I'm going to take you through spherical coordinates. So from the evolution of coordinates, we started from Cartesian, we moved to polar, right? From polar, we moved to cylindrical, and finally we are on spherical. So we've tackled this, and this in our previous lectures. If this is the first time you are visiting this channel, kindly subscribe and please do well to turn on the notification button so you get updated when I post new videos. So we moved from Cartesian XY or XYZ. Okay, we move to polar, and polar is strictly r comma pi comma theta. Then we move to cylindrical, r theta then z. Then finally spherical. So what are we expecting for spherical? So to go into spherical coordinates, you can see the trend of complexity. So the more we move to the higher dimension, the more our plane gets more complicated. Okay, so now let's see. So I'm drawing a 3D. I have my y, I have my x, and I have my z here. Take note, when we say spherical, we are dealing with space. Okay, spatial space, meaning that it's three-dimensional, an object acting in space. So this is what I'm going to say. The parameters of spherical coordinates is rho, comma, theta, comma, phi. This is it. So these are three important parameters we need to find. Rho, comma, theta, comma, phi. Okay. So at this point, the next thing to do is what are the representation? How do we find the component, which is rho, what is theta, and what is phi? So as I said earlier, in spherical coordinates, we are dealing with a point in space, okay? So we will have a point acting in space. It's neither in the xy plane, neither in the xz plane, neither in the yz plane. So the line that joins the origin to this point in space, okay, is going to be represented as the rho. That's the magnitude, is the rho. And remember, let me make this here. When I reproduce this line on the xy plane, you realize that the image of this point, which is in space on the xy plane, will also have a similar fashion r and what theta, right? You realize that this point in space will have an image here. So in the xy plane, this point will also have the magnitude from the from the origin to the r, and the angle from x is theta, right? So what we're going to do is we want to find the parameters. Now we know that p is representing the magnitude from the origin to the point in space. Theta is the normal theta we know. When I say normal, I mean the polar form, the theta, and also the cylindrical form, which is always giving us the tan inverse of my y coordinates over my x coordinates. Okay. Now, what is rho? Rho is the absolute magnitude. Okay, and you realize that this point in space here will have an angle to the z-axis, and that angle we will name it as phi. Okay, so in the raw sense, this point in space upon rotation about our z-axis can form a shape like a cone in this form. Okay, if this point, depending on the angle here, if this was supposed to be somewhere here and this forms a rotation or revolution about it, it also creates a sphere or a hemisphere. So I'm trying to give you the idea of the spatial nature of spherical coordinates. So it's the value of this phi, which is the angle our point is making with our z-axis when this angle keeps on widening. So when this happens to fall at the down here, so if I have this point coming down here, you realize that after rotation about the z-axis, or after some kind of revolution, you're going to get a complete sphere. So that's the concept of spherical coordinates. For that reason, this phi you see here can only have values starting from 0 to pi. So the maximum it can go is what? Pi. So once our point here, this line, which is the line joining the point and the origin, once it assumes the 180 degrees, and after revolution it was going to form a complete sphere. So the largest geometric shape you can ever get is a sphere. Okay, that's a sphere. When you have a 3D, yes, a sphere is going to be the largest dimension you get, because the angle which you are making with the z-axis can rise from 0 to pi. So meaning that my phi lies from what? 0 to pi and doesn't exceed any. So what is rho? So since I have phi here and I have rho here, I want to define my rho here. So when I join this line here, you realize that when I take my rho cos this angle, that gives me my what? Horizontal here. And that horizontal is parallel to the r here. When I take this p sine my phi here, it's going to give me this side. Okay, it's going to give me this side. So you realize that see, let's reproduce this one here down here, so that I get the z-axis acting somewhere here, let's say z, and I have the p moving this way, and I have the phi, then the rho is here. So this side represents what? The horizontal, and that will take rho cos phi, and this side will take what? Rho sine what? Phi. Is that not it? Yeah. So what I'm trying to show you is here, this side is simply rho cos phi, this side is rho sine phi, and you can clearly see that this part here is parallel to our r down here, meaning that our r is simply equal to rho sine phi. Then you can clearly see that this side, which is the z, is that not it? This side, which is the z, is equal to my rho cos phi. Therefore, my rho itself is equal to the square root of what? Z squared plus r squared. Is that not it? So now you realize that my r squared is the same as what? S squared plus y squared. Then you add a z squared to it. Therefore, rho is generally equal to the square root of the square, the sum of the square of each x, then y, then z. That's all. So this is a nice concept, which is three-dimensional space spherical coordinates. So giving you a wrap up, spherical coordinate has three components: our rho, comma, our theta, then our phi. As I said, our rho is generally giving us the square root of what? S squared plus y squared plus z squared, or in simple terms, square root of r squared plus z squared. The next thing is our theta, and I said theta is the same as that as polar and that as cylindrical. Okay, so because of that, I'm going to have tan inverse of y on x. Then my phi, which is what I have here, my phi. So to get a phi, we are going to use the relation that my r is equal to rho sine phi. So from here I can find phi, or else you can also use your z is equal to rho cos what? Phi. And here too you can find what? Phi. provided you know what your z and your rho. So this is the basic things you should expect in spherical coordinates. So now let's take a nice short simple example here. So convert the cylindrical coordinates. So let me cancel this side. So convert the cylindrical coordinates into brackets square root of 6, comma, pi on 4, comma, square root of 2. We are converting this to spherical coordinates. Sorry. So we are converting this to spherical coordinates. So how do we do this? To convert this cylindrical coordinate to spherical coordinates, what you're going to do is you ask yourself, what are the parameters of spherical coordinates? I only need my rho, comma, theta, comma, phi, right? What is this I have here? This cylindrical coordinate. And you know, cylindrical coordinate has r, has theta, then z, right? So I can say that my r is equal to root 6. I will say that my theta is equal to pi on 4. Then I'll say that my z is equal to square root of 2. And from this information given, I can go ahead. I know my theta. My theta is here, right? But what is my rho? Remember, rho is given as the square root of r squared plus z squared. So I'll simply bring here square root of 6 all squared plus my z square root of 2 all squared. This is giving me square root of 6 plus 2, which is square root of 8. Now I know my rho to be square root of 8. Then the next thing to do is I need my phi because I already know my theta. And I now know my hot rho. I need my phi. So my phi, as I said, is equal to rho cos hot. So my z is rho cos phi instead. You can use that to find it, or else. So you have either z equals rho cos phi. You can also say that your r is equal to rho sin hot phi. Any of them should give you right answer. Or you can also divide these two equations so that you can see that let's say r equals rho sine phi, right? This over z is equal to rho cos what phi. Is that not it? So we can get our r over z to be equal to rho and rho go away, you get tan phi. Is that not it? So meaning that the tan inverse of my r on z should give me my hot rho. So let's try these different possibilities. So I'm going to have tan inverse of what my r, which is given as square root of 6, over my z, which is given as the square root of 2. So that should give me my phi. So when I simplify this is the same as tan inverse of what? Square root of what? 3. Is that not it? Because you're going to have square root of 6 on 2, which is the same as square root of 3. And tan inverse of square root of 3 is simply 60 degrees. 60 degrees. That is pi on 3. Okay. 60 degrees. And let's see. Here z is what? Root of 2 is equal to rho, which is what? We had root of 8, is that not it? Cos phi. So then, so let's see. I'm going to have here to be cos phi is equal to root of 2 on root of what? 8. So cos inverse phi should also be equal to cos inverse of what? Here I'll get root of 2. Let me maintain is root of 8. So let's punch this into the calculator. So cos inverse of root of 2 root on 8, and that is also giving me 60 degrees, which is pi on 3. So that is how we do it. So writing our final answer, we simply have our rho, which is square root of 8, comma theta. In the question, we got theta directly from the question because theta in the question was pi on 4. So I simply write pi on 4. Then my z2 will turn into what, 5, and the 5 was pi on 3. So this becomes the coordinates, which we call cylindrical coordinates. Thank you for being with me in this video, and please don't forget to like, subscribe, and share if you find this helpful.